Okay, so this is a case study. Just so you know, Cognetics Engineering did not design that particular 3D printer. It's something that we own, and it's an excellent means to teach about integration of components because it's got several components integrated into it. But it is a 3-axis automated system based on the Cartesian system. So that means X, Y, Z, 3 linear coordinates, okay? Something that's interesting, a topic that we're going to introduce to you today as well, is even though you have a system whose components and alignment is not very precise, you can still design it in a way that once everything comes together, the output can be higher precision. So just to give you an idea, the framing components, the aluminum extrusions that form the frame of this 3D printer, they're not very precise as far as perpendicularity. So the whole thing is skewed to some extent, but the output, the precision of the printing head is fairly accurate. Okay, we'll talk about that more later. This 3D printer is not exactly a custom component in the sense that they designed it and only 1 up to 10 are built. Obviously, the volumes are higher than that. But the principles and what we're going to go through today are applicable to custom components, which are like 1 to 10 units or so. And then also low, mid, and high volume production. All right. So a lot of components that we're gonna be talking about here. So we've got shafts for guidance and support, linear bearings, as I mentioned before. And this particular system integrates recirculating ball bearings. And in 2 different forms, one of them being the linear pillow block bearing. Lead screws are used, 2 of them, alignment couplings, timing belts and pulleys, stepper motors. There are no servo motors in this design, just stepper motors. But the mechanical integration principles are the same or very similar. We'll talk about snap action switches, proximity switch, and of course the framework, the framing of the system having to do with brackets and aluminum extrusions. So before we move on through this slide, let me pull up a browser here. Just remember, along the way, we like to also show you where you can find, where and how to find components, etc. So let's do a quick search here. Aluminum extrusion. Let's look that up. And just select images for now. Okay, and all of these are extruded aluminum components. You can see that a lot of them are designed for framing purposes, and there are different geometries, different profiles. So that was the frame. Now we start to talk about the linear motion components. And of course, there's a z-axis, x, y, z, 3 axes. And the approach that they use for the design and production of this 3D printer is to use round rails for linear guidance. On the left, obviously, that's a round rail or a shaft. Okay, and next to it, they're showing a recirculating ball bearing that fits that shaft and slides in a linear motion. It advances and returns. On the right side is what they sometimes they call it a square rail. We call it a square rail. It's not very squared, but that's the term that's commonly used. And again, an equivalent recirculating type of linear bearing to match that geometry. The one on the right tends to be able to withstand a lot higher loads. It's stiffer and stronger, but also more pricey. The cost is higher. All right, so let's talk about this here. Recirculating ball bearings, including linear pillow blocks, And let's see, in the next slide, we're going to be talking about binding. It's a very important topic in mechanical design. Okay, so in order to drive the z-axis upward, for example, since there are two lead screws, left and right, I'm going to grab the alignment couplings and turn them both at the same time, turn them clockwise. And you can see that, I hope you can see that the z-axis is going up very slowly. I'm not going to do it, but if I were to only turn one of them, the x-axis would start to get skewed. It would start to go up like that to a point where it stops moving and it starts probably damaging or bending the guidance system, because both of them need to turn at the same time for it to smoothly go up and down, maintaining as close as possible to a 90-degree angle. You have a recirculating ball bearing riding on a shaft. The balls inside are rolling, doing their best to eliminate the friction or minimize the friction between the bearing itself and the shaft. So over the bearing, well, you install the bearing into a housing that you use as a carriage or as a slider. Okay, so this is the housing here. This component moves up and down. Okay, this is the round rail in there. What you see there is the recirculating ball bearing. And in this design, there happens to be two of them. So I'm going to back up a little bit. Okay, there's a recirculating ball bearing here and another one below. And you have the same thing on the other side. You can see them right there. Okay, one above, one below, inside of this housing. The housing has multiple functions. In the case of linear motion, binding happens under certain circumstances, and the end result is there's too much friction and the linear motion gets stuck. So binding in simple terms means that you have something that's supposed to move freely and it gets stuck because of too much friction or too much load or improper design. So just real quick again, each of the axes on this system have two round rails, right? One up here, one down here, both parallel to each other. The z-axis on rail here, rail over here, parallel to each other. But the z-axis is much farther spread apart than for example, the x-axis. Okay. Let's go back to Andy's question for a moment, because that kind of helps us address binding. Let's say there was no lead screw here, or no lead screw here on the left, okay? That lead screw doesn't exist. There's a bearing here. There's a bearing here. Both of them have two recirculating ball bearings, okay? But as far as the driving component, there's only one lead screw. Is the minimum. So let's go ahead and explore that rule of 2 to 1 is the minimum. And let's say that in our design, we're aware of the issue. And okay, just like the z-axis of the 3D printer, we install another bearing here. Exact same one. And we make the housing a little bit bigger so that it can hold that bearing. Now looking at the length to diameter ratio, we are approaching 2 to 1. Let's say it's exactly 2 to 1. So now the friction points in a binding situation are farther apart. I'm just going to do this here. But still, if the torque arm is this long, way over here to this red component on the right, that's still very risky. So two main ways to address binding. There are many, but two main ways to address binding. Number one is shorten the torque arm as much as you can. So let me highlight that real quick. So make the torque arm as short as possible. That's one way that helps eliminate or minimize the possibility of binding. Yeah, I would agree. It's around there. Could be close to 3-to-1. Okay, good. But you guys, I think you're seeing the difference, right? If we only look at one shaft at a time, the bearing ratio seems to be, let's see, close to 4-to-1, one shaft at a time. But the system combined is more like the other way around. Wait, bearing length to, right, it's more like 1.5. It's the other way around if we look at it combined. So this 4-to-1 no longer applies. All right. It was very important to spend time explaining this. Now we can move on to the printer itself, have a look at it, but we have a better understanding of what's going on as far as guidance. Okay, when we talk about lead screw profiles, it's basically the geometry of the thread. So if we were to take a close-up there, there's a specific geometry for those threads, okay? But alignment couplings are there to compensate for misalignment between components. Okay, so the reason these are handy is that they are multiple piece couplings. As usual, you have a bore or a hole on the left, a hole on the right for the shafts that you're working with. But the coupling is able to separate for assembly, for servicing, etc. It separates. So that comes in handy many times. And a lot of these are zero backlash. You don't have to worry about that. And they're fairly good for angular misalignment and parallel misalignment. Not necessarily very good for axial misalignment. Approach to eliminate backlash by using a spring. So in this case, the spring expands the length of the lead screw. And you can see that by doing that, the nut is going to grip the lead screw tighter because of the force applied by the spring.